So the whole idea of subsets and elements and things like that. So this is not the same thing as this, right? This is A, which might itself be a set. This is the set that contains A as an element. Okay, so A is a subset of A. A is not an element of A. A is an element of the set that contains A. A is not a subset of the set that contains A. All right. I think in Principia Mathematica, Bertrand Russell reduced, or I guess Russell and Whitehead, reduced all of mathematics to the empty set and sets containing the empty set. So this is a little bit of culture. So how do you build up the integers out of the empty set? So you have to have this notion of a one-to-one mapping. So you represent 0 by the empty set itself. That set has no elements. Okay? How do you represent 1? You need a set with 1 element. Well, what is that element going to be if all you have is the empty set? That element will be the empty set. Okay, so this is deemed to be sort of equivalent to 0. That set has 1 element, namely the empty set. Okay? How do you make the number 2? You need a set that has 2 elements. What could those 2 elements be? Well, one of them could be the empty set, and the other one could be the set that contains the empty set. So this is the number 1, and the number 2 is this set which contains the empty set as one of its elements, and the set containing the empty set as its second element. So that is equivalent to the number 2 in this representation. Okay, so they build all of mathematics from the empty set and sets containing the empty set. All right, so if A is a set, it might be empty, it might have elements, it might actually have some elements, but it's not the same thing as the set that contains A as its element. This is a collection of sets. Right? It's a set that has as its only element another set. Right? Does this kind of make sense? No, it doesn't make sense. Okay. Think of a set as a bag. All right, you've got stuff in the bag. So here I have, and let's say A is the set. It's a bag with 1 apple in it. Okay. This set is a bag which has inside it a bag with 1 apple in it. The element of this set is a bag with 1 apple. This set is a bag with 1 apple. Right? So the set is the bag and the stuff in it, as it were. Okay, so this set contains a bag with an apple in it. So it has this as an element. Okay? This is not a subset of that, because because it's an element of it. It's not a subset of it, right? It's not itself the kind of things that are collected here. Well, I mean, you can think of an element of a set as being a subset of size 1, but it's a slightly different notion. So in this Russell-Whitehead notion of building up mathematics out of the empty set, this is an empty bag. This is a bag that has an empty bag in it, right? There's something in it, an empty bag, right? This set is a bag that has in it an empty bag, and then a bag that has inside it an empty bag, right? So this is 2 bags. This is 1 bag inside another bag, right? There's 3 bags inside, but you can't tell them apart, right? The empty set there's only 1 empty set. So you can't put the empty set in the set twice. It's already in once. It's in forever, right? There's only one of them. So what makes this element different from this element is that this is a bag around a bag, and this is just a bag. Okay.
So that has two elements?
This set has two elements.
So you only go down one level. You don't care what happens.
Well, what are the elements of the set? This is one of the elements. This is another element.
Okay, so you only go down one level. You don't care what's inside those elements.
Well, they might. I mean, this happens to be a set of sets. Those sets have elements, but this set is not the same as this one. These are two different elements of the bag. Okay, this sort of doesn't really make sense because in a set, if it has the empty set in it, that's it, right? It has it in once. It's sort of like it doesn't make, if you're in the classroom, you're in the classroom. There aren't more copies of you around, right? There's sort of just you. All right, does this kind of help? Yeah. Sorry? 3, yeah. So 3 would be, we have, what are the 3 elements? We have the empty set, we have the set that contains the empty set, and we have the set that contains the set that contains the empty set. Okay, we have an empty bag, a bag that isn't empty, it contains an empty bag, and another bag that isn't empty, it contains a bag that contains an empty bag. Okay. Okay, I mean, this is weird, and you're not expected to know it or whatever. This is just cultural stuff, but it maybe helps you think about what's the difference between a set and the elements of the set, or a subset of the set. So the empty set is a subset of every set, right? But in this case, a subset of this is this. This is a subset of this set. It is this element, right? It corresponds to this, the set that consists of the empty set. The set that contains the empty set. Okay. So this is a subset of that. All right. Let's do just a couple minutes to try to tie this to probability, which is where we're going in another couple of lectures. So this universal set S that we've been talking about and using for Venn diagrams, when we start talking about random experiments and probability, S is going to be the collection of all things that could possibly happen as a result of the experiment, all of the possible outcomes. It's called outcome space. And what we will call events are subsets of outcome space. So this is outcome space. And an event okay, so for instance, our experiment could be toss a coin 10 times. So there's an experiment. In a row. Okay, so what would outcome space consist of then? What can happen when you toss a coin 10 times? So we could actually think about this a bunch of different ways. There are a bunch of different ways of sort of turning this into a piece of math. But if we really care about whether you get heads or tails in each toss, then an outcome, what can happen as a result, is a sequence of heads and tails of length 10 in all. Okay, so one thing that could happen is you could get heads, heads, heads. Is that 10? Okay, so that is one outcome. It is an event. Okay, it's a simple outcome. It's one thing that could possibly happen. We could also get all tails, or we could get heads, tails. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Should probably end with tails if it started with heads and it's even. Yes? Okay. All right. So an event is a subset of outcome space. These are particular outcomes. what is an example of an event in this case? An event might be the event that you get 2 heads in all. Okay? So one example of an event might be, we'll call this A, is the event that you get 2 heads in all. Okay, so what subset of outcome space does that correspond to? If outcome space is all sequences of 10 heads and tails, sequences of length 10 comprised of heads and tails, what does A actually look like? We've written it in words, but how would we write it in terms of these outcomes?
Head and 8 tails? Is that what you're saying?
Okay, so the subset of outcome space that corresponds to getting 2 heads and 8 tails, right? It has a bunch of members. There are a bunch of different outcomes that all correspond to that event occurring. One outcome that corresponds to that event occurring would be heads, heads, and then 8 tails. Okay, another outcome would be heads, eight tails, and a head, right? How many of these elementary outcomes are in this event? You got 10 places. 2 of them need to get heads in them. There's 10 choose 2 ways of picking which 2 of the 10 places get heads. So there are, in all, if we wrote all of these down, there would be 10 choose 2 sequences of heads and tails that have, sequences of 10 heads and tails that have exactly 2 heads. So in this event, this subset of outcome space, there are 10 choose 2 elementary outcomes, sequences like this. Does this work for people? Okay, when you think about an experiment and asking whether a particular event occurred or not, one thing that I find useful heuristically is if you think about the outcome space as being a dartboard, and you throw a dart at the dartboard, and if the dart sticks in the event, then the event occurred. All right, so I toss 10 coins, and if what happened was I got one of the sequences that contains 2 heads and 8 tails, then the dart stuck in this event, which is exactly 2 heads happening. If the dart stuck outside there, that event didn't occur. Okay, so lots and lots of different events. So what about the event that you get at least 1 head? How would that be represented here? Would it be would it contain this? Would it be a subset of that? Which is more restrictive, getting exactly 2 heads or getting at least 1 head?
No, getting exactly 2.
Okay.
Getting exactly 2.
Getting exactly 2 is one of the ways you can get at least 1, right? You could get 1, you get 2, you get 3, you could get 7, you could get 10, right? So getting at least 1 is less of a restriction than getting exactly 2. Getting exactly 2 satisfies the restriction of getting at least 1. So the event of getting at least 1 is going to contain this.
It's like the complement of 10 tails, right?
Yeah, it's everything but 10 tails. Yeah. Okay? So now, if I throw the dart and the dart sticks here, that means that I got at least 1 head, but I didn't get exactly 2 heads. Okay, so you think about what events occurred. If the dart stuck here, this less restrictive event occurred, but the more restrictive event didn't occur. If the dart sticks here, both of the events occurred. The dart stuck in both of them, because getting exactly 2 heads implies that you got at least 1 head. When you think about these things, what does it mean for one event to imply another? In this pictorial representation, it means that if the first event occurred, the second must also have occurred. All right? So in this representation, there is no way for the dart to stick in the event that you get exactly 2 heads without it also sticking in the event that you got at least 1 head. Right? It's a subset. So one event implies another event if it's a subset of the second event. People often get this backwards. Right? So okay, does A imply B or does B imply A?
B implies A.
Yeah, B implies A. There's no way for the dart to stick in B without it also sticking in A. Okay? What about here? Does A imply B? Does B imply A? Neither one, right? Because the dart can stick in one without sticking in the other. It can stick in both at the same time, but it doesn't have to. Okay? All right, so I think you now know what you need to know to do the homework for tomorrow. At least, well, whether you know it or not, I don't know, but at least I think I've covered it. So, okay. Are there any questions before we go on? Oops. Yeah.
One more time go over the difference between mutually exclusive and independent.
Mutually exclusive and independent? We haven't gotten to independence yet. Nope. We'll be there in a couple of lectures. I'll go over it in depth then, but we need probability before we can talk about independence. Other questions? Yes?
So A is a subset of the set that contains A?
No, it's an element of the set,
It's an element. Okay, so it's not.
not a subset. So to be a subset, it has to be itself a set, right? So the set that contains A is a subset of the set that contains A. But A is an element of the set that contains A. All right, we're on to talking about propositional logic, which is basically how you mathematically combine statements that can be either true or false using logical operations. So the fundamental entities that we have are propositions. So a proposition is a statement that can either be true or false. Okay, and I'm typically going to use letters like P, Q, R, S to denote propositions as variables that stand for propositions. The letter F stands for the proposition that is always false. And the letter T stands for the proposition that is always true. So we're going to write various functions down. So there's a very close tie between set theory and propositional logic, and we'll explore some of that a little bit later. But we'll start by talking about this stuff in terms of logical operations. The most fundamental logical operation is negation, logical negation, not. Okay, so negation. So, and we're going to, negation takes a single argument. It operates on one proposition at a time. And basically, it turns false into true and true into false. Okay, so one way, so the symbol for negation, you see this sometimes, you see minus, you see exclamation mark, you see a tilde. These are all symbols. We're going to use the exclamation mark almost always. So Basically, it's defined as follows. Not true is equal to false, and not false is equal to true. That's what it does. That's what the operation does. It just negates the truth value. Takes the opposite. OK, so it takes one argument. All right, what's the next kind of operation that we might consider? Well, one of the other building blocks is or, disjunction. So or, sometimes it's written with a vertical bar. Sometimes it's written with a little v. We're going to mostly use the vertical bar. OK, so it takes two arguments. It's an operation on two propositions. And what basically operates this way. True or true is true. True or false is true. False or true is true. And false or false is false. All right. So we're going to start representing these tables, these truth functions in terms of tables. So what we have here, for example, is let me see exactly how I've done the notation in the book so I can be consistent with it. So P, Q, P or Q. So if P is true and Q is true, then P or Q is true. True, false, true. False, true. True, false, false, false. So there's a truth table for the logical operation or. Okay? When P takes the value true and Q takes the value true, P or Q, that's true or true, takes the value true. This so far so good? It's all stuff you've probably seen before. Okay. Yeah.
So why does, for the two in the middle, why does true always outweigh the false?
That's the definition of or.
Oh, that's the definition.
We are defining what or means. So this is, so far it's definition.
Yeah.
Yep. Okay. All right. Conjunction. So conjunction, which sometimes and sometimes written as a wedge, sometimes written just by writing the things next to each other, almost like you can write set. Oh, let me take 2 minutes. Well, let me finish this, and then I'll take 2 minutes to talk about why the notation AB for the intersection of the sets A and B is natural in some sense. Okay. All right. So the truth table for conjunction for and is P, Q, P, and Q. Okay. If they're both true, then this is true. Otherwise, it's false. Okay? Or is true if either is true. And is true if both are true. Okay? This is a definition. Right? There's no mystery here. It's just how it's defined. So far, so good? Okay. Everything else in propositional logic can be built up out of negation, disjunction, and conjunction. So take negation and an or. But there are a bunch of other symbols that can be reduced to this. Let's talk about them briefly. So, for example, implies, or if then. And this is sometimes written with an arrow. Okay, so P, Q, if P, then Q. What's the truth table for this? Well, if P and Q are both true, this is true. If P is true and Q is false, this is false. If P is false and Q is true, this is true. And if P is false and Q is false, this is true. Okay, this is, again, a definition. This gets back to when the chapter we're talking about in reasoning and fallacies, right? If A, then B. So you can either think of this as just a definition, or you can try to relate it to real life and ask why, for example, is this thing not false? Right? So we're saying if A, then B. How do you show that that would be a false statement? Well, it has to be the case that A happened and then B didn't happen. Right? If A didn't happen, all bets are off. The statement doesn't tell you what's going to happen. Right? So this is like if it's sunny, I will wear sandals. Okay? So in order to refute that, it has to be sunny and I don't wear sandals. If it isn't sunny, then you can't refute it. It doesn't matter whether I wear sandals or not. It's not contradicting anything. Okay? All right. This is, in fact, logically equivalent to what? When is this true? This is true whenever Q is true, right? And it's also true whenever P is false. The only time it isn't true is if P is true and Q is false. So this is actually logically equivalent to Q or not P. All right, what does it mean for two propositions to be logically equivalent? It means that they take exactly the same truth values under the same circumstances. So if I plug in any value for Q and any value for P and evaluate what that gives me, it's going to give me the same thing as if I plugged that value of P and that value of Q into this expression. So what happens if I plug P is true and Q is false into here? I get P is true, not P is false. I have false or false, which is false, right? So if I have P is true and Q is false, this gives me false. P is true and Q is false, that gives me false. They're logically equivalent. They take exactly the same truth values. Okay? Now, how many, so these are truth tables involving two propositions being combined in some way. How many such truth tables are there in all? Right, I've listed here 3 of them. One of them is for P or Q, one is for P and Q, one is for P implies Q. But if I did something really complicated like not Q or P implies Q and P or not Q. Yeah, I could write something really, really, really complicated involving P and Q. Yes? And in principle, that would give me some other truth table. When I plug in a value of P and I plug in a value of Q, I get some answer out. How many different truth tables are there if I have 2 propositions going in? Okay, we have 4 as a suggested hypothesis. He said with a tone of voice that implies that it's possible that might not be the right answer.
You said if you have 2...
Got 2 propositions going in, and then some function of their truth values coming out. Right? Well, this table has 4 places in it, right? There's 4 combinations of true and false for P and Q. Yes? And then for each of those, I have how many possibilities for what the value is that the function takes? 2, right? This could be true or false. 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 Right? So how many different truth tables are there for 2 propositions going in? 2 to the 4th. Yes? There's 2 possibilities for this, times 2 for that, times 2 for that, times 2 for that. Right? Okay? So there are 2 to the 4th, which equals what? 16? 16 truth tables for 2 propositions. combine. Okay, one of them is true, 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 true. It's just true no matter what the input is, right? That's a function of P and Q that just always gives you true. There's another function of P and Q that always gives you false. There's another function of P and Q that gives you true, false, false, false. That's that one. There's one that gives you false, 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 true. There's one that gives you true, false, true, false. I mean, there's 16 different possibilities. And you can write them all in terms of negation and an or. All right, so let's see if we can actually build one of these for entertainment's sake. All right, let's somebody come up with what we want the right-hand side to look like, and then we'll try to come up with an expression that gives us that. What, sorry? All true? Well, that's easy. That's just the function that returns true. So that's you know, there are many things that are logically equivalent to that. So, for example, P or not P. Right? That's always true. That's an example of something that has this truth table. Okay. All right. How about a harder one? True, false, true, false. Okay, so this is one that is true whenever Q is true, right? And it's false otherwise. It's true exactly when Q is true. So this is logically equivalent to Q. Right? It's a function of P and Q whose value is Q, whatever Q happens to be. How about another example? True, true, false, false is just P. Yep. How about true, false, false, true? Okay. This one has a name. All right. When is this true? This is true if both P and Q are true or if both P and Q are false, right? So we can write that as P and Q or not P and not Q. Yep.
So it's either both of them or?
Neither. Both or neither. Yep. Okay. So this thing has that as its truth table. It's true if both P and Q are true. It's also true if both P and Q are false. But if only one of them is true, then both sides are going to be false. So it'll be false. Now this is actually the truth table for if and only if, which is written as a double arrow, like that. So this is the same thing as, this is logically equivalent to P if and only if Q. That's what its truth table looks like. That's what this means. That's what this symbol means. It translates to that. This is also equivalent to P implies Q and Q implies P. Sorry. And, not or. Yeah. What happened to not P and not Q? What do they look like? This one, this whole expression evaluates to this, right? If we plug in true and true, we get that this is true, and therefore the whole expression is true because we have true or false, which is true. That gives us this line. Suppose P is true and Q is false, then P and Q is false. Not P and not Q is also false. We have false or false, which is false, so that gives us the false. Similarly here, these are both going to evaluate to false, and that'll give us false. But if they're both false, P and Q is false, not P and not Q is true, because that's true and true. Not false is true, and not false. So that's true and true. This evaluates to true. That gives us this row. Was that the question?
Also, you combine disjunction and conjunction for the function.
Yeah, this is sort of a complicated function of P and Q that only involves negation, disjunction, and conjunction.
Yeah.
And this is its truth table.
Okay.
Okay, it is one of the 16 possible truth tables.
So you combine, yeah.
Yep. Yes.
So, that definition, would that mean if P implies Q and then Q implies P as well?
Yeah. So this is saying that these are all logically equivalent things. So this is a truth table. This, if you like, is a definition of if and only if, a definition of this, the double arrow. It is defined to be that. Okay, that is its truth table. P, if and only if Q. Okay, and this is if P then Q and if Q then P has the same truth table. Let's look at that. So if P then Q, right, that's going to be true if, we can do two things at once here. One is we'll evaluate this by plugging in values. That's one way to try to evaluate a complex expression. Another way is to try to reduce it by putting in, by making substitutions that are identities. Okay, so what happens if P is true and Q is true? So that would evaluate to true implies true, and true implies true, right? Which evaluates to true and true, which evaluates to true. Right? So over here, it has the right value. When both P and Q are true, it's correct. What happens if P is true and Q is false? Then we have true implies false, and false implies true. True implies false is false. False implies true is true. False and true is false. So we get back this. Yes?
I don't need this back here, but is there a way to explain why false and true is false, or should we just memorize it as false and true is false?
Why false implies true?
No, at the very, like just false and true is false.
Oh, well, and means they both have to be true.
Right. Like for, some of them are like less intuitive and like kind of filtered.
It really is. It's a definite. What does it mean for and? It is sunny and I'm wearing sandals. That is false. If it isn't sunny, it is false if I'm not wearing sandals. They both have to be true. Yes.
Why does false imply true? Why is that true? Does that false imply true?
Okay. So the question is, why does false imply true? True. And one answer is that's how it's defined. Its truth table is, true, 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 false, false, true, false, false. Sorry, I'm not being consistent about this. What is this? What is the implication? I'm sorry, I'm not even writing this right. Okay, true implies true is defined to be true. True implies false is defined to be false. False implies anything is defined to be true. And the heuristic behind it, if you want to try to relate it to the real world, is if you want to refute the assertion that if it is sunny, I will wear sandals, you can only refute that if it's sunny, right? If it isn't sunny, then it doesn't matter whether I'm wearing sandals or not. You can't sort of falsify my assertion. It has to be sunny, right? So this assertion can't be false if its premise is false. Is that okay? And there's a question in the back. This is if and only if. This is a different truth table here. This is not if then. This is if and only if. We started with this and said, what expression will give us this as an answer? For for P implies Q, it's this. P, Q, P implies Q. Okay, so if you like, you can take this as a definition. You can take it as the definition that it is logically equivalent to that P implies Q is logically equivalent to not P or Q. So it has the same truth table. Now, logically equivalent can actually be written as this if and only if sign. Because what does this mean? This is true exactly when both sides are the same. So this is true if both P and Q are true. It's true if both P and Q are false. And otherwise, it's false. Right? That's what this says. It's true if both are true. It's true if both are false. Otherwise, it's false. So another way to write this is that P implies Q if and only if is logically equivalent to not P or Q. They are logically the same. You also write them as equal as functions. As functions of P and Q. All right. So this one strategy for figuring out what the truth table of this is was to plug in a value for P, plug in a value for Q, and see what you get. And that's what we just did. We just did two examples. We plugged in both of them true. We plugged in P true, Q false. Right? A different way to evaluate a complex compound proposition is to try to do some algebra with it, as it were, some logical reductions. So let's try that strategy. All right, so if P then Q and if Q then P. So if P then Q is logically equivalent to not P or Q, right? Not takes higher precedence than the conjunction and disjunction. So this is not P or Q. It's not the same as not P or Q. That's a different thing. The not happens first. Okay. And what? Not Q or P. Yes?
For the ors in this, does that mean that it's only P or only Q, or it can also be both?
No. So remember, the truth table for or is P, Q, P or Q. Okay, this is the truth table. So it's true if either of them is true or both. There's an exclusive or operation that comes up in computer science and some things a lot, but it's not. Yeah, this or, as long as one of them is true, then or is true. Sort of defined by this truth table. One way to think of or, if you think of true as being equal to 1 and false as being equal to 0, then or is like the maximum. Okay, so then sort of what's the maximum of two things that are either 0 or 1 is 1 if either of them is 1 or both. And if they're both 0, then the maximum is 0. Okay, and can be viewed as multiplication in this context. A and B is true if you represent true by 1 and false by 0, and you multiply the things together, the product is 1. Right? So if either of them is 0, the product's going to be 0. If both of them are 0, the product's going to be 0. The product's only going to be 1 if they're both 1. Okay, so and is like multiplication, or is like taking the max. Right, this actually brings us back to the thing I said I was going to talk about briefly, which is why the notation A, B makes sense for intersections of two things. So if you think of this as a function that is equal to 1. So if we represent, there's this notion of indicator functions. We're going to write IA of some number, of some value x is equal to 1 if x is in A, and it's equal to 0 if x is not in A. So this is the membership function or indicator function of the set A. Okay? So similarly, IB would be the function that takes the value 1 for elements of B and takes the value 0 for things that aren't the elements of B. Okay? So what is the indicator function of the intersection AB? So the indicator of AB is equal to 1 if x is in A intersect B, and it's equal to 0 if x is not in A intersect B. Okay? I want a function that's equal to 1 if x is in the intersection of A and B. Well, what happens if I multiply together the membership function of A and the membership function of B? So I have IB of x is equal to 1, x is in B, 0 otherwise. Okay, IA times IB is going to be equal to 1 if x is in both A and B. And otherwise, it's going to be equal to 0. Because if either of these is 0, if you're not in A, then IA is going to be 0. 0 times whatever this is going to give you 0. If you're not in B, then this is going to be 0. 0 times whatever this is going to give you 0. You're only going to get 1 if you're in both of them. So IAB is, in fact, equal to IA times IB. And this is why this sort of multiplication notation for intersection makes sense. Because the membership function, the indicator function for the intersection, is the product of the indicator functions for the two sets separately. Again, this is just a cultural nuance. You don't have to remember this. It just might help you understand where the notation comes from. All right, let's go back to this because we need to learn some rules for how you distribute negation, conjunction, so forth and so on. They're rules that are very much like De Morgan's rules for sets that apply in logic as well. In fact, they're called De Morgan's rules for logic. Okay, how do I combine the ands and the ors and the nots, right? I need to know how I do algebra with this stuff. Okay. Let's look at some general rules. So what would not P or Q be equal to? P or Q is true if either or both is true, right? Okay, it's false only if both are false. So if I want to negate that, okay, so if I want to negate it, I have something that is true when both P and Q are false, and otherwise it's false. Okay, so this is not P and not Q. Okay, what about not P and Q? Okay, so this is true only when they're both true. Otherwise, it's false. So the negation is going to be false when they're both true, and true if either of them is false. Okay, so that looks like not P or not Q, right? And there's sort of parens around this, except that negation takes precedence over these other operations. So we don't need to do that. Yes?
Can you explain the logic? I know that because I know the already filed, but like I don't understand.
Okay, well, so we can just work it out. So where's it come? Well, we can just work it out, all right, to show that these two things really are logically equivalent. So let's go over what piece of board should I use?
How to work it out as well.
Well, I mean,
Or is it better?
it's really, so what does the truth table look like? So if we have P, Q, P or Q, not P or Q. True, 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 false, false, true, false, false. P or Q, we've got true, 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 false. This is false, 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 true. Yep. And then we look at what this is. Not P and not Q. What does its truth table look like? I didn't save enough room to write it here. Let me try to. Okay, so if P is false, so not P and not Q. So not P in this row, not P is false, not Q is false, false and false is false. Yep. Okay. In this row, P is true, so not P is false. True, so we have false and true, which is false. Okay, here we've got true and false, which is false. And in the last row, we have true and true, which is true. So it just has the same truth table. They just are equal. I mean, that's what they're logically equivalent statements. Okay. And this is one of the 16 possible truth tables. There are many other things that have this truth table, because you can continue to combine P and Q with and, or, and not, as long as you like. And it will whatever you get is going to evaluate to one of the 16 truth tables for two things. If you had three things, there'd be more of them. Before we go on, how many truth tables are there if you had three variables, P, Q, and R, you were combining?
81.
Bigger number, something. Okay. So how many rows would there be in the table?
Rows?
How many rows would there be in the table if we had P, Q, and R? We have all combinations of true and false for each of two variables, right? So there's two truth values, right? We've got two truth values for P. For each of those two truth values for P, we have two truth values for Q. For each of those, we have two truth values for R. It's 2 times 2 times 2, right? It's fundamental rule of counting. It's 2 cubed. Okay? So there's 2 cubed rows in the truth table for something with P, Q, and R. For each of those rows in the truth table, there's 2 possible values. It could evaluate to true or it could evaluate to false. So it's 2 to the power 2 cubed. Okay? So the number of truth tables with P, Q, and R would be 2 to the 2 cubed possible truth tables. And in general, if we had k variables, it would be 2 to the 2 to the k possible truth tables. Okay. Some of them are really simple. All true, all false, etc. Some of them are more complicated. Okay. All right, so these are sort of how does negation distribute over and or, but we need another thing as well, which is how do you distribute and or over each other. So what is by themselves and or each satisfy associative and commutative properties. So P and Q has the same truth table as Q and P. And P and Q and R is the same thing whether you group it this way or not at all. It's going to have the same value, and it's the same thing as P and R and Q and so forth. Similarly, P or Q has the same truth table as Q or P, and P or Q or R is going to be true no matter how you group, is going to have the same truth value no matter how you group the terms. Okay, so these are sort of associative and commutative, but what about here? We need to evaluate something a little bit more complicated. We have combination of and or. How do you combine P and Q or R? Okay. This is just like A intersect B union C. It is just like that. Okay? So it's either P and Q. This is true if either Q or R is true, but P has to be true no matter what. Right? So this is P and Q or P and R. Right? Okay. What about P or Q and R? Okay, this is just like A union B intersect C. Right? And is like intersection, or is like union. Yep. So this is P or Q, and helps that I write what I'm saying, P or R. Right? Just as a sanity check, no matter what. Okay, so if P is true, this is true, right? No matter what Q and R, whether Q and R are true or not. Is the same true on this side? Yeah, because if P is true, P or something is going to be true. P or something is going to be true. We'll have true and true, which is true. Right, just sanity check, yes? Okay. All right, how do we use this stuff now? We have all the rules we need to try to simplify this further. Yes?
Just a quick question. What if Q is magic plus Q and R are both false? Because like P is true.
If Q and R are both false, P or Q, but P is true, then P or Q is true or false, which is true. And this is also going to be true or false, which is true. So, yeah. Okay. All right. So now we've got this funny combination of ors and negations and blah, blah, blah. Can we somehow simplify this using these sort of algebraic rules for combining stuff? Well, let's try something, right? What can we do? We could call this one object, and that's that and something or something. Yes? And so this and something or something is like this and something or something. We could apply this rule for the sake of argument. You see where it gets us. Yes? So what happens if we apply that? We get that and something or something is this and this, or this and that. Right? So what does that look like? Kind of running out of board space. Maybe. The question is simplifying it. We'll see where we get. Okay. So using this rule, this becomes not P or Q and not Q, or not P or Q and P. Yes? So far, so good? Okay. Look at this. This is not P or Q and not Q. How can this possibly be true? Yeah. The only way for this to be true is if not P is true and not Q is true. Right? So the Q here isn't helping. It's not changing anything, because the only way for this part of the and to be true is if Q is false. If Q is false, then this is something or false, and that doesn't help. Does that make sense? Yep. So this piece is really the same as not P and not Q. Does that fit? Okay, suppose Q is true. Then this is false, and as a result, this whole expression is false. Right? Because this is something and false. Suppose Q is false. Well, then this is true, and the whole thing becomes true if not P is true. So this whole thing is true if both P and Q are false. It can't be true if Q is true. Okay? So we have this or. What happens here? Well, it's exactly the same thing. In this case, how can this possibly be true? Well, if P is false, then we've got something and false, and this is going to be false. Right? So the only way that this side can be true is if P is true. So then, if P is true, the only way this piece can be true is if Q is true, because P isn't helping. So this side is P and Q. Same thing. P and Q or Q and P is the same thing. Yep. Right. The stuff. Okay. So this was the first expression that we wrote down. Right. That's this. Right. I mean, again, or we can flip things around. So. Okay, so starting with it represented this way, we've now shown by algebra that it's logically equivalent to this, which is where we started.
I know we started with the bottom one.
Well, we started with this truth table, and then we came up with this as a way of expressing the truth table, and then said this is actually a shorthand for that the way the if and only if is defined is it's defined to be this. Then I asserted that if and only if was equivalent to saying P implies Q and Q implies P. And what this was just simply showing, yes, indeed, that's right. We showed that it's right two ways. One way we showed that it was right was by plugging in values of Q and P and showing that we get this truth table back. And here what we did was did some algebra to show that, in fact, we get the formula back. Okay, two ways of showing the same thing. Okay. All right, those two strategies are really useful for evaluating compound propositions. One strategy is simply plug in the possible values of Q and P and see what you get. The other strategy is do some reduction, do some actual logic on it. All right. The chapter has in it some exercises that will generate random logical propositions and ask you to evaluate whether they are their truth table, or find a find a corresponding proposition. So should we do one really complicated one? Yeah, all right. While I'm erasing, remember we had this notion of an argument, a valid argument, and a sound argument back from the chapter on reasoning and fallacies. And we're going to hit that stuff again in this chapter. A valid argument is one where if the premises are true, the conclusion follows as a matter of logic. A sound argument is one where if the premises are true, the conclusion follows as a matter of logic, and the premises are in fact true in the real world. Okay. All right, so somebody want to just call out some complicated proposition and we'll evaluate a truth table for it? I'm going to make something up. I could do this one. This is what is that? Okay, here is the question here is to write a proposition that is logically equivalent to the following. Not, open paren, Q implies P, close paren, or, open paren, not Q or not Q. 1, 2, 3, 4. And open paren, not R implies not P. Oops, not P is in paren. Sorry?
We have to turn your paper this way.
Turn the paper that way, yeah. Sorry. Implies not P, 1, 2, 3, or open paren, not open, not R, open paren, not open, not R, or not R, or not R, close. 2, 3, 4, 5. Okay. I don't even know if the parentheses balance. Can somebody tell me? Okay. This is horrible. I mean, it's horribly complex, but it actually isn't hard. All right? Not R or not R. That simplifies, doesn't it? What is it? Not R. Not R. R. Okay, so all this stuff out to there already reduces to R. Yep? Okay. Am I even going to be able to tell where these parentheses are supposed to be? Okay. We've got not, R implies not P. Okay, the assignment here is to get rid of the if-thens and turn this into something that just involves and, or, and not. So R implies not P is logically equivalent to not R or not P. Okay, so this is not R or not P. Okay, but we are now negating that. How do you negate a conjunction? A disjunction, sorry.
How is that not R, not P?
P implies Q is logically equivalent to not P or Q. Okay, so R implies not P is logically equivalent to not R or not P. Yep. Okay, we're now negating this, right?
Not
Okay, so this negation is applying to both of these guys. We're negating this or this, which is not this and not this. Okay, so this is, that evaluates to R and P. Okay? So this whole thing here becomes R and P. Okay, so we have R and P or R. What does that evaluate to? This is only true if both R and P are true. This is true whenever R is true. So for this to be true, this has to be true. Right? And so this whole thing is just logically equivalent to R all by itself. In order for this to be true, both R and P have to be true. But if R is true, this is true. And if this is true, this whole thing is true whether P is true or false, because you've got it true on the right-hand side. Is that okay? So this reduces to R.
I would have done R and P in some ways. I don't know why.
Well, okay, so R and P is only true if R and P are both true. But this thing is true even if P is false, as long as R is true.
Why can't it reduce to R, but why can't it also reduce to R and P?
Because this is true even if P is false, but R and P is not true if P is false.
I think I don't know.
Well,
I don't know what's negating P. I think that's the problem. I understand the R, but I don't.
okay, we need to consider what happens when R is true, what happens when R is false, what happens when P is true, what happens when P is false. Okay, if R is true, this whole expression is true by virtue of the right-hand side. Okay, no matter what P is. If R is false, this expression is false, because false and whatever P is still going to be false, and this is still going to be false. So the only way that this expression is true is if R is true, and if R is true, this is true, no matter what P is. Is that, yes, question?
Yes, it has one thing. Is it always assumed that only R is always true? What if it's not R? Is the beginning
No,
very...
if R is false, this whole thing is false.
Yeah, I understand. The innermost expression, not R, right?
Yeah?
What if not R is not false?
Then it's true.
So it's going to give the same.
But we're finding something that's logically equivalent. It's a function of P, Q, and R. So we're finding another function of P, Q, and R that no matter what combination of truth values we plug in for P, Q, and R is going to give us the same answer as the original expression. So it's like, saying we could write something as, x squared minus 1, or we could write it as x plus 1 times x minus 1. Right? They're equivalent. No matter what the value of x is, the left and the right are equal. We're trying to find an expression, so no matter what the values of P, Q, and R are, we get something that's equal to what you'd get if you plug P, Q, and R into this. Okay? All right, so this whole thing evaluates to R. What about this? Q or not Q? True, right? Q has to be true or false. Can't be neither true nor false. If Q is true, this is true because that's true. If Q is false, this is true because that's true. So no matter what, this is true. Okay, so then we're going to negate true. No matter what, that's false. So that's not helping with the or at all, is it? Because anything or false is just whatever the original thing was. Okay? So this whole thing, yeah, this isn't contributing anything.
Anything that's seven or false
Is the first bit, right? Because it's true only if this is. The other part isn't helping. So what's this? This is not Q or P. Okay. And R. So I'm not sure where the parentheses go here. That's negating this. That's actually negating this piece, isn't it? Okay, so what's the negation of not Q or P? It's not this and not that. Right? So this piece becomes equivalent to Q and not P.
Wait, why not Q and not?
Well, it's already not Q. We're negating the not Q to make it Q. Right? Okay, so we have Q and not P and R. That's the whole thing. So that whole mess reduced to Q and not P and R. Those are logically equivalent, if I did the algebra right. I think I did. I can try plugging it in to see, since I have this to test myself, though. Q and not P and R. Oops. Went away. Okay. What else do we want to cover here? All right. So remember, one way of thinking about an argument is it has a list of premises. Premises are propositions. They can be either true or false. And the argument is valid if, whenever the premises are true, the conclusion must be true. So I might have a premise that says P is true, a premise that says if P is true, then Q is true. Okay? And then the conclusion of my argument might be therefore. So therefore is sometimes done with 3 dots or with something like that. Therefore, Q. Right? That's an example of a valid argument. It has 2 premises, P, and if P, then Q. And the conclusion is Q. All right? Another way of writing this, another way of checking whether the argument is valid is whether the conjunction of the premises implies the conclusion. So that's saying, another way of saying that, so if we have P and P implies Q, does this in fact imply Q? So if no matter what you put in for P and Q, this thing evaluates to true, then the argument is valid. Okay? If there were a combination of P and Q that makes this whole compound proposition false, then the argument isn't valid. Because the claim is that if these 2 things are true, then this must be true. Right? So can we do some algebra on this to see whether this is in fact the case? Well, P and Q. Sorry, P and if P then Q. Sorry, I said it wrong. So this is P and not P or Q. Okay. What if P and, is this going to help the truth value at all? The not P? No. The only way this can be true is if P is true. If P is true, that's false. So we have false or something, which is just the something. So this evaluates to P and Q. Right? So we've got P and Q implies Q is where we are right now. Sorry, this was just this being reduced. Okay. So this implies this is either not that or that. Right? So we have not P and Q or Q. Okay? So yeah, so not P and Q is not P or not Q, right? So we have not P or not Q or Q. But now we have this is true if Q is true, because then this is true. And this is true if Q is false, because then this is true. So this always evaluates to true. It's just true. Does that make sense? So this argument is logically valid because the premises taken together, the conjunction of the premises, does indeed imply the conclusion as a matter of math. Okay? Now, if the first premise were I am an alien, and the second is if I am an alien, then the sun goes around the earth, then this is logically valid, but it isn't sound because at least I don't think I'm an alien. But, okay. All right. The only other thing to mention briefly before we go is that there's this connection between logic and set operations that you can sort of think of. What is it? P as being a subset of things that can happen, and P is true means that one of those things indeed happened. So if I represent the proposition P by some subset, and I represent the proposition Q by some other subset, then P, the logical expression P or Q is represented by the union of these two things. The logical expression P and Q is represented by the intersection of these two things. The logical expression not P is represented by the complement of P. Right? So there's a really close connection between the set theory and the propositional logic. Right? And ultimately, all this stuff is going to be useful for the probability. Are there questions about this? I mean, it's like messy algebra, but conceptually, it's just true and false. Yes?
Can you go over the last one again, just why not P or not Q or Q?
Sure. Okay, so remember, so the question, go back over this again. So remember, for or, the parentheses are really redundant. Okay? So we could actually group this way. This is not P or not Q or Q. That's true. Anything or true is true. So that's true whether P is true or false. Yes?
What do you get from the Q to Q to the next step?
This? This is still this Q.
But how do you get from there to the next step?
From there to there? Okay, so this is, you can think of this as if X, then Y. That's logically equivalent to not X or Y. Right. Okay. Other questions? Well, I'm heading to office hours. I'll see some of you there, and I'll probably get email over the weekend from them.
Angry.
Right.
Very angry.